And also this is a kind of a culminating topic, which means that everything that you've learned before will be used in this topic. Okay, so let us start. You can refer to my notes on how to go to Mars in the lecture note channel. Okay, so this is the problem. Yeah, let's say you're from Earth, you want to go to the Mars. So please take note that we will be interchanging our gravitational parameter. Yeah, if you still remember, our gravitational parameter for Earth is 398,600 kilometer cube per second squared. Okay, so now because we are doing an interplanetary trajectory, so all our trajectories are heliocentric. Heliocentric, which means let me write this down here. Okay, so it's heliocentric, which means it's centered in the sun. Helio means the sun. Okay, so if you need to calculate the Hohmann transfer, for example, you need to use mu of the sun, which is that 132.71 times 10 to the power 9. Okay, so do not be confused. I think a few your senior batches, you know, when we were doing their final exam, they always use the mu 398,600, which is actually for geocentric orbit. But now, because we are doing interplanetary, going from planet to planet, we are going to use the mu of the sun, gravitational parameter of the sun. So that is clear, yeah? So the other thing is, what we are going to do is basically, well, how to go to Mars is just a fancy title for this lecture, but actually the more technical word for that is a Patched-conic approximation. What is a Patched-conic? Okay, first let me explain to you what is conic. So we learn of 4 types of conic orbit. Okay, one is circular orbit, another one elliptical orbit, parabolic orbit, and hyperbolic orbit. Okay, so conic, if I say conic, then that is what I meant by that. Now Patched-conic, what does it mean? It means like this. If you want to launch a spacecraft from Earth to Mars, okay, to Mars, so you have to actually separate the conic orbits. What I'm saying here is, when you are doing analysis here on Earth, okay, you need to use a different conic orbit. You need to use, in this case, you need to use a hyperbolic orbit, because we are shooting our spacecraft far ahead, like to Mars. It's really far. Okay, so in this case we cannot use elliptical orbit, because elliptical orbit here, then you'll just go around the Earth. You need to use hyperbolic orbit, because you need to launch yourself to distance very far away, which is Mars. Okay, and then when you launch a spacecraft from the Earth orbit, when you get into the heliocentric transfer orbit, here we are going to use another conic, which is ellipse, because remember our Hohmann transfer, if you use Hohmann transfer, yeah, so our conic orbit is an ellipse. This is an half ellipse. All Hohmann transfer ellipse is an half ellipse. So this is another conic orbit. And then when you arrive here in Mars, when you do analysis, you use hyperbolic orbit again. So this is what Patched-conic approximation means. We approximate that our analysis here, okay, we assume that here it's hyperbolic, and then when it goes through the heliocentric frame, we use the elliptical orbit, and then when we arrive here, we do our analysis based on hyperbolic again. So so that is why it's called patched. You got 3 patches here, 3 different kind of orbit. Okay, so let's look at it in a simple way first. How do we transfer a spacecraft from Earth to Mars? A simple explanation. would be just to use Hohmann transfer. Easy. You already know how to use Hohmann transfer, but the only difference right now is you use mu of the sun. Okay, not anymore 398600, which is mu of the Earth, gravitational parameter of the Earth, but now you use gravitational parameter of the sun. Everything else is just the same. How to calculate delta V1, how to calculate delta V2, how to calculate apogee and perigee. Everything must be focused on the sun. So RA, for example, will be the distance from the sun to the Earth. Okay, our apogee, for example, will be the distance from the sun to Mars. Okay, so is this clear for everyone? I think you can do this, yeah? Okay.
Yes, Doctor.
Okay, so now let me show you a trick. Not a trick, but there's one thing that we need to figure out when we were launching our spacecraft from one orbit to another. So let me show you this to you. Okay, so this is how it's going to look like. Okay, I hope you understand that. It's because when we launch our spacecraft, not only the spacecraft is moving, but also the planets are moving, right? So ideally, you want to launch your spacecraft, okay? You want to launch a spacecraft such that when it arrives in the Mars orbit, the planet is there. Okay, you don't want to be arriving here and then planet Mars is somewhere, I don't know. That will be useless. Then you'll be stuck in this orbit chasing Mars forever. Okay, so that is what we have to figure out later on. But like I said to you, let's take this one by one. Okay, let's figure out the simple things first. The basic, I think everyone knows this. This is just a Hohmann transfer. We have done this many times. Actually, we have done bi-elliptic transfer, all the more complex stuff, plane change maneuver. But here, let's just simplify the situation. Let's say we are launching our spacecraft from Earth to Mars in a Hohmann transfer ellipse. Okay. Now, before I suggested to you that you need actually to calculate delta V1 and then calculate delta V at perigee, V circular orbit, yada yada yada. So right now I think you have understood that very well. So right now it's time for me to just give you the formula to calculate delta V1 and delta V2. Okay, so these are the formulas where this distance here, this one is called R1. Okay, so this is big R, R1. Okay, R of Earth, and then R2 is obviously the distance from the center of the sun to the center of Mars. So that is R2. Okay, so don't be confused. So I think you can solve this straight away. You just need to find what is mu sun. You need to know what is the radius of the distance of radius of from sun to Earth, radius of that orbit, and the radius of the Mars orbit. Okay, we assume, I forgot to tell you this, we assume that both planets' orbits are circular. Okay, so we can use Hohmann transfer. Okay, so this is very clear. I give you the formula straight away. You can just plug it in and then get delta V1, delta V2. Okay, now you can plan a Hohmann transfer from Earth orbit to Mars's orbit for an optimum 2-impulse maneuver. Okay, so this is done. I already given everything here, so now you can do this. Easy. Okay, in just 5 slides, I've explained to you how to launch a spacecraft from Earth to Mars. Sadly, it's not that easy. Okay. Calculate the heliocentric. Okay, so this is an exercise for you. I think this is pretty easy. You can calculate the heliocentric departure speed, which is delta V1. Okay, and time of flight for Hohmann transfer from Earth orbit to Mars orbit. So if someone asks you, how long does it take to get from Earth orbit to Mars's orbit? So the quick way, you can just tell them this time of flight if you're using Hohmann transfer. Okay, that is the optimum ideal time of flight. It might take longer than that. Okay, so now you can do this easy. Now, like I said before, it's getting harder. We've only figured out how to move a spacecraft from Earth's orbit to Mars's orbit. How do you plan the maneuver such that you reach the planet at the arrival time? Let me bring you back to this here. How do you make sure that when you launch the rocket, right, the spacecraft, when the spacecraft arrives in Mars orbit, the planet is there, okay, and it's not somewhere else, okay? So the idea is you need to launch your spacecraft at the right time if you want to use Hohmann. Okay, you need to time your launch. You cannot just launch today and expect it to be there when Mars is there using Hohmann. No, you need somehow to figure out the launch condition, the launch window, when to actually launch your spacecraft. Okay, so let's look back at this here. So let's answer this question: how do you plan the maneuver, the Hohmann maneuver, such that you reach the planet, not just the orbit, reach the planet at the arrival time? Okay, the short answer is we need to start our Hohmann flight at the right phase angle, which in other words, we need to start our launching procedure at the right time. How to find the right time? Okay, so let me bring you to phase angle. What is phase angle? Okay, so don't mind all these nomenclatures yet. So let's look at this. Okay, what I'm doing here is just a general non-hohmann maneuver. Okay. Oh wait, someone's calling me. Hold on, yeah. Okay. If you look at this, don't worry if it's not Hohmann. You can see a bit of angle here, not 180 degrees. Don't worry about it. This is just a general form. Okay, the phase angle. Okay, how to calculate the phase angle is this phi 1. Phase angle meaning the angular difference between the position of the Earth and the position of Mars. So the angular distance between these two is called phi 1. Okay, so to answer the question again, how to make sure that when you launch a spacecraft, the spacecraft arrive on the planet, on planet Mars. So you need to find the right phi 1, right angle. Okay, so if the angular difference between Earth and Mars is phi 1, then you can launch your spacecraft using whatever transfer you want, non-hohmann or Hohmann transfer, whatever. Okay, so now I'll give you a formula here, but let me explain one by one. A total sweep angle. Okay, how to find here? What we want to do is we want to find the right condition time. We want to find phi 1. Okay, first we need to know the total sweep angle. Sweep angle is this. Okay. Oh wait, let me check. Mars needs you. Okay. Everyone is still here, yeah? Huh? Yeah.
Yes.
Oh, okay. All right. Okay.
Yes.
Bye. So now, we need, what is total sweep angles? Total sweep angle, it meaning that when you do the transfer, the angle of that Hohmann transfer ellipse. If it's non-Hohmann, then your delta theta will be less than 180 degrees, right? Okay, will be less than pi, correct? So if its Hohmann transfer is with perfect Hohmann, you launch in periapsis or perihelion and then arrive at aphelion, then you're going to this delta theta will be pi or 180 degrees. Okay, so we can just if you are doing Hohmann transfer, then delta theta will be pi or 180 degrees or 180 degrees. Okay, let's put that here. Alright, so don't worry about that. So okay, we need to calculate this. We know this for Hohmann, this value is 180 degrees. Okay, minus the mean motion of Mars. Okay, so what is the mean motion of Mars? Mean motion is you can think of it as also the angular velocity of Mars. Okay, you can always find it online. What is the mean motion of Mars? Okay, okay, there you go. This is in degree per day. But you can look at our textbook, either our Curtis textbook or Bate, Muller and White textbook. You can find the mean motion of Mars. But this one is, you can find this. Okay. So when this is easily found, it's okay. So next thing is delta t. So delta t is the transfer flight. That means you start here and you arrive here. What is the time of flight? Now, if you still remember our orbit as a function of time, okay, when it's less than 180 degrees, it's kind of hard to do that. You need to use the Kepler's equation. You need to use your orbital time of flight calculation, right? So if it's non-hohmann, general non-hohmann, then you have to use all this Kepler's equation again. Remember the paper that you've done, the Newton-Raphson? Yes. But if it's Hohmann transfer, so this will become easy. If it's Hohmann transfer, then the time of flight here will be equal. So for Hohmann, so will be is just P of the transfer ellipse okay, divide by 2. Okay, easy. If it's Hohmann, then it's easy, you can just do that. So back again here. So if you are looking at delta t for Hohmann transfer, you just need to calculate the period of this red orbit here and then divide by 2. So that's your delta t. Okay, if it's a non-Hohmann, then it's going to be a little bit complicated. You need to use the Newton-Raphson method. Okay, so this is how to find the right phi 1, the right launching condition, the right launch window. So this is the formula. Okay, so I'll stop here at the moment, and if there's any question I can attend to. Okay. Let me put this on here. Okay. So I'll just give a few seconds. Oh, YB is typing. So method E can be used. Yeah. The method can be used for other planet as well. If you want to go from Earth to Neptune, Earth to Saturn, okay, but usually, practically, if you want to go to faraway orbits, it's better to use what we call a gravitational assist. You go the long way. You need to go around the sun first, and then with the help of gravity trajectory, whatever, and then you can go there. So usually, that's why I said here for this one is for mission from Earth to Mars. If you need for mission from Earth to Pluto, for example, you might take a more complex trajectory. Can you use this method to go from Earth to Venus, for example? Yes. The answer is yes. You can use the same Hohmann maneuver to go from Earth to Venus, except because you've learned how to use Hohmann for to reduce your orbit altitude, yeah. So you can do that also. But for this moment, let's figure out how to go from Earth to Mars, because this is our most immediate destination, I guess. Okay. If you're talking about much of Voyager, yes. So just to answer your question, yeah, just this is an easy way. For basic, you need to actually know how to do this patched-conic approximation. But if you want to go to faraway orbits like Pluto, for example, okay, you can see it's really complicated. Let me show you here. Okay, you start from Earth. Let me show you here. Okay, why is it dark? Let me show you here lah. Okay, so if you want to go to Pluto, well, Voyager's spacecraft's destination is not really Pluto. It's just to go as far as possible. So if you need to go to somewhere as far as possible, you need to actually, start your hyperbolic orbit here and then go through an orbit, something like that. You use other planets to actually adjust your orbits. Okay, it's more complicated here. This one, is this a GIF file? Yeah, it's better to use a GIF file here. Okay, this is a Voyager. Okay, you can see the pink one. That's how you see every time it kind of crosses the orbit of a planet, the direction changes because the gravity of the planet is pulling the spacecraft also. Okay, so this is a more complex maneuver. Okay, we will learn about this also. But currently we are doing how the simple maneuver of just going to our neighboring planet. Okay, can we use also landing on asteroid? Yes, you can. Yes, if for example the asteroid is actually orbiting the sun. Okay, asteroid orbiting the sun. Yeah, you can use the same procedure, but there's a but. There's a lot of it's not that it's not as simple as this. Yeah, for asteroid, for example, it doesn't usually asteroids are very small. So when it's small, it doesn't have a strong gravitational attraction, but it's not zero either. Okay, so when you do the Patched-conic approximation, for example, you can start with hyperbolic orbit and then go through a elliptical heliocentric transfer. But when you arrive at the asteroid, this hyperbolic orbit might not be as ideal as what we've learned now. The reason is because asteroid doesn't really have a strong gravitational acceleration. Okay, and so you might have to use some other method. So actually, spacecraft has been launched onto asteroids and stuff like that. So it's quite easy to do that. Actually, you just remind me. I did. You can check. I'll send you a cute video on this one. Rosetta Mission. Okay. Yeah, Rosetta. Okay. Rosetta. What was the name of the Philae? Okay. So you can watch this cute video on how we launch a spacecraft.
Once upon a time, a spacecraft named Rosetta.
We're gonna watch this after the class, I think. Okay. It's pretty cute. Okay, so we figure out now how to do Hohmann transfer from Earth to Mars, and how to figure out what time it is actually the right time to launch our spacecraft using Hohmann transfer. Okay. Now for Hohmann transfer, everything is easy. Delta theta will be pi or 180. I better not use over here. better use or, just to not confuse everyone. Okay, now for the delta t also easy, is just p over 2 transfer ellipse here. Okay, the red one, don't forget. So transfer ellipse, let me make that one red. Oops. Okay, red one, yeah. Okay, okay, so we don't really care about phi 2 though, because but unless if you want to do some kind of maneuver, like you want to return back to from Mars to Earth, then probably we need to find phi 2 and use the same method. But right now our mission is just to go to Mars. Okay, so everything is nice, everything is ideal, but what if we miss the opportunity to launch? Let's say we miss, we figure out phi 1, say phi 1 whatever delta whatever theta degrees, for example. Okay, we got phi 1 degrees, that's the opportunity for us to launch our spacecraft to Mars. Let's say we missed it for some reason, I don't know, maybe we don't have enough funding opportunities, or we slept over, I don't know, whatever reason we miss the opportunity to launch. So how long do we have to wait until the correct phase angle again? So if we miss now, how do we know the next time is gonna come? When? Like you miss the bus, how are you gonna know the next, when is the next bus is coming? Okay, unlike our bus system, we couldn't figure out what time they are coming, because even if we have timetables and everything, they are all useless. So we need to find what we call a synodic period. It depends on the synodic period between two planets. What is a synodic period? Okay, a synodic period, I wrote it as P sin. P synodic is the time required for any phase angle to repeat itself. For example, if the right angle is phi 1, okay, we need to launch that, and then we miss that. So how long do I have to wait for phi 1, that phase angle difference, to happen again? So we can use this formula right here. Okay, all right, I'll give you another formula here. There's a if you don't like to use mean motion, you can use this formula too, equivalent to p planet 1, whatever that is, times p planet 2, okay, divided by, let's insert p of planet 1 minus p of planet, planet 2. Okay, so let me make it small. So you got two formulas there, you can use either one. Okay, so how to find the synodic period? So you need to actually find this number. So I think the number is around 700 days or something, if I'm not mistaken. You have to check that again. So if you miss that launch opportunity, probably you're gonna have to wait for another 2 years or so. Might be wrong on the number of days though, but you can check it yourself, yeah, using this formula. Okay, so that's what happened. That's the time that you have to wait if you miss the launch opportunities. Okay, let me stop here. There's sadly there's no grab. We have to actually to wait 2 years. Let me check. I think it's 2 years. Oh, by the way, if you are looking for another extra reference on textbook, you can look at Curtis chapter number 8. Okay, interplanetary trajectories. It's the same thing. If you are using the other book, Bate, Mueller, and White, the Fundamental of Astrodynamics, I think it's also in chapter 8, section 8. Yeah, yes, same thing. Okay, probably the nomenclature is a bit different, but if you have both books, you look at chapter 8. It's the same thing. Okay, you can look at this formula as well. All right, so I think we have done everything. We have done this. Okay, how to actually, when to launch. Okay, we know that. When to launch, the question first, when to launch, you need to wait when the phase angle between Earth and Mars is equal to phi 1. What is phi 1? That's the formula right here. Okay, to input all that numbers. Okay, now how to calculate the delta V here? Easy, I gave you the formulas already, so you don't have to actually find circular orbit speed lah, perhaps perihelion speed, aphelion speed. You don't have to do that. I give you a formula also. Oh, by the way, let me write here, perihelion. We are using perihelion and aphelion. Okay, before we use perigee and apogee, right? Okay, so we use a new nomenclature, which means the focus is on the sun. Okay, so how to find? Okay, we know when to launch. We know how much we use to launch. Can we know how long does it take from Earth to Mars? Yes, that's the easy part. You already have your transfer orbit here. You calculate the period of this red orbit here and divide by 2. I think most of our question for an interplanetary Hohmann transfer orbit is already done. Okay, now so we can do this now. Okay, so we know when to launch and we know how long does it take to arrive. Okay, so if there's any question, you can type it in before we go to the next headache. Okay, the next headache will be, just now it was simple. You know how to use Hohmann, everything formula is given. Now it's another headache. You remember I talked about Patched-conic, yeah? So far what we have learned is about this middle conic here, the ellipse. Okay, that's easy, we've done that. But let's check what kind of analysis we should do in this region when we want to actually launch our spacecraft from Earth so that it goes into a heliocentric orbit like this. Okay, jang jang jang, we have to use hyperbolic trajectory. Okay, now, so what we've done so far is establishing the heliocentric transfer orbit, but how do we get out of a sphere of influence? Note this word, sphere of influence, and into the interplanetary trajectory. Let me explain to you. Sphere of influence meaning if you are within the radius of influence, the sphere of influence around Earth, okay, where if you're within Earth's sphere of influence, your motion will be dictated or will be controlled or will be subject to the Earth gravity. Okay, so we need to know how big is the sphere. How big is the sphere such that your spacecraft is still under the influence of Earth gravity. Okay, so in order to do this transfer, you need to get out of Earth's sphere of influence. You need to get out there. Okay, so that's why we need to use parabolic orbit or hyperbolic orbit to get out of there. Remember, parabolic orbit or hyperbolic orbit is an orbit where you go and never come back, pergi tak kembali. Okay, so to get out of Earth's sphere of influence, you need to use hyperbolic orbit. So that's why we are doing this here, conic orbit here. Okay, hyperbolic. Now, the answer is how to use hyperbolic orbit. So once you have determined delta V1, okay, we can establish the injection near the surface of Earth, which will result in a hyperbolic trajectory towards Mars. Okay, so delta V, don't worry, I've already given you this here, this delta V. So once that is calculated, now what we need to do is we need to establish this orbit here so that the spacecraft can go to Mars. Okay, so let me explain this diagram here. Okay, as you can see, this is Earth. The focus is there. Okay, the red orbit is the hyperbolic trajectory. We need a hyperbolic trajectory because we need to get out of Earth's influence, radius of influence, sphere of influence, sorry, and then to go to somewhere far away, which is Mars, and we need to use hyperbolic trajectory. Okay, and you can imagine the position. Earth's sphere of influence is somewhere far away, somewhere really far away. I don't remember the numbers though. They should be hundreds of thousands of kilometers. Okay, so if you're within this sphere of influence, that means your spacecraft is still under the influence of Earth's gravity. Once you get out of there, then your spacecraft will be subject to the sun's gravity. Okay, so just to imagine to you, Earth is also moving around the sun. Yeah, so Earth is moving that way. You can imagine here like this. Earth is moving that way. Okay, hopefully you can see my cursor. This Earth is going that way, so that's why Earth's orbital velocity is that way. Okay, truthfully, the Earth is going around a big circle around the sun. Okay, but we can do that velocity vector like that. Okay, and this is heading toward the sun, just like here. Okay, here this is Earth's orbital velocity, and this is direction towards the sun. So that is how the hyperbolic trajectory is going to look like. Okay, all right. So how do we establish such hyperbolic trajectory? Before that, let me stop for any question. No question. Okay, can I continue? Okay, now you look at this. Let's say this is Earth orbit and your Mars orbiter or Mars spacecraft, Mars rocket, whatever, is currently resting, not resting, parking in this orbit here. It's parking in an orbit around Earth first before right now it's waiting to be launched to faraway destination. Right now it's just resting in this orbit. Okay, I don't want to use the word resting. Resting means doesn't move, but it's parking in this orbit. It's orbiting the Earth. Now it needs to be given another big delta V here, so that it will change its orbit into a hyperbolic trajectory. Okay, so you have your circular orbit velocity here, and to get into this hyperbolic trajectory, you need to find velocity at the perigee. Remember, velocity at the perigee for hyperbolic orbit. I carefully use perigee here because we are still in Earth's influence, perigee. Okay, so we need to find VP later on, because to do that we need to actually find this trajectory first. So how do you find VP? Okay, you need to know V infinity. What is V infinity? We call V infinity is the extra speed that is required to escape the gravitational pull from massive body. Okay, let me ask you here. What is the minimum speed to escape Earth's gravity? What is the minimum speed? I'm not asking about numbers, but can you tell me what kind of speed is the minimum to get out of Earth's gravity? Huh? Is it a parabolic orbit? Let me see. So, parabolic orbit velocity, okay, is the minimum velocity to escape Earth's gravity. If you still remember this. Okay, remember it's what was the speed again? I think square root of 2 mu Earth, divide by 2. Divide by, wait. Divide by r. Doesn't appear as nice. Okay, so this is the parabolic orbit velocity to escape the minimum. This is the minimum. Okay, so if you have this, then you just have just enough to go to escape Earth's orbit. Okay, so in this case, if it's a parabolic trajectory, then V infinity will be 0. So V infinity is the excess speed. Okay, that means if you are on hyperbolic trajectory, that means you're gonna have that as V infinity. Okay, so how do we calculate V infinity? Okay, so I have provided some explanation here. Note that delta V1 that you've calculated before represent the speed of the spacecraft relative to Earth upon exit from the Earth's sphere of influence. Okay, it is the hyperbolic excess speed left over after the spacecraft escaped from the Earth. So you can assume V infinity is equal to delta V1 that you have calculated here. Oops, here. Okay, here. So this is your V infinity. You can assume that safely. Okay, so you can calculate this. Now you can calculate the radius of influence if you want. I've provided you some formula here. R meaning R radius of planet towards the sun. So I didn't. So okay. Alright. So R is the distance. This is mass of the planet and this is mass of the sun. Okay? So you can use this. Now, you already know how to calculate. This is the important part, to know V infinity, that is to know the hyperbolic excess speed, that is the most important part, because remember this, we're going to use this a lot. Next, that's next. Remember, we need to calculate VP and whatever. Okay, now velocity VP to get into hyperbolic orbit trajectory is defined by the hyperbolic excess speed squared plus 2 mu of Earth, so that I don't confuse you right there. Mu of Earth, not mu of Sun, divided by RP, perigee, whatever your parking orbit is. Okay, so whatever your parking orbit, let's say the parking orbit has a radius of 10,000 kilometers, why not? If it's 7,000 kilometers, so that is the radius of perigee here. Okay, the lower the better, because when you are lower, this speed here is fast, so you can launch faster. Okay, remember that's probably I'm gonna ask you later on. It's better to start fast so that you can launch fast easier. Okay, and then you already calculated this V infinity, which is delta V1 square root, you know mu of Earth, easy, divided by RP. RP is whatever this is given usually. Okay, your parking orbit, that's your VP. Now the actual first impulse at departure, okay, your actual delta V1 to actually escape Earth orbit to go to Mars is this. Okay, where VC Earth is the orbital velocity of circular geocentric parking orbit, this one here. Okay, so delta V departure is what you need to calculate to get into this another conic. So we are talking about this conic right here. Okay, so that's the thing. So I give you another formula right here also to calculate the eccentricity of the hyperbolic trajectory. You can use this. Okay, all right. Now you know it's a hyperbolic trajectory. You know its eccentricity by this formula. You know how much. You know the delta V at perigee. V at perigee for the hyperbolic orbit, and then you know how much you need to actually push yourself, delta V departure, to push yourself from this parking orbit into that hyperbolic orbit. It's this. Now you need to know when, you need to know where you need to launch your orbit. Where is the location of the perigee of the hyperbolic orbit? Okay, so it can be done here. Let's say this is this line here, horizontal line, is the direction of the Earth's orbital velocity. Okay, the angle between Earth orbital velocity, the horizontal line, and the line of perigee, beta, can be calculated using this. It looks nasty, but basically is beta is arc cosine of 1 over E. Okay, and if you need to calculate this eta, I don't think you need to, but I think the other book uses this. The other book uses eta, so you can find this. Okay, so now you know how much you need to calculate, and you know where, how much to push yourself, and where do you need to push yourself. Here, beta, where, and how much is delta V departure. Okay, so now you are here, you push yourself, you use this extra delta V departure, boom, you are on this trajectory already, and now you're ready to go into a Hohmann transfer ellipse, heliocentric. Okay, so this is how you launch yourself from Earth. I will end here, and then I will ask you this question. Now we have departed from Earth. What to do when we arrive in Mars's orbit? So you can imagine we need to do another conic analysis in Mars, and it's going to be a lot more complicated than launching from Earth, because here in Mars you need to actually get into Mars's orbit in the right way, right distance. You don't want to be too close to Mars because you'll be crashing on Mars. So there's a lot more parameters that we need to look at.